Here it is, bridge rectifier. Next session as about rectifier, third circuit, bridge rectifier. So previous section full wave rectifier, and previous than that was about half wave rectifier. So in a continuous session we had completed half wave rectifier and full wave rectifier using center tap. So what was the drawback of full wave rectifier? It was dependent on center tap transformer, correct? So specially designed. The central tapping is not at all easy. Okay, so that is difficult to make the central winding to be tapped and make it available for ground voltage. So that is a difficult task. Okay. Second, its cost, and the problem that is to be overcome is the main target of this bridge rectifier. So here it doesn't use center tap transformer. In previous circuit there were 2 diodes, here it uses 4 diodes. So about a bridge rectifier, bridge, yes, that connects 2 ends. So here it is, the bridge rectifier with normal transformer step down that uses, here by observation we feel it's like a parallelogram. So here point A and point B, 2 points are connected through 4 diodes, that is called as a bridge rectifier. So first point about the positive half cycle of this secondary voltage. Whenever A end becomes positive, B end becomes negative. So A end is positive. Here let's observe the polarities across each diode's terminals. Anode of D1 becomes positive, but cathode of D4 becomes positive. From negative terminal B, cathode of D3 becomes negative, but anode of D2 becomes negative. So which diode will get forward biased? Anode receiving positive or cathode receiving negative? Anode that receives negative or cathode that receives positive will not work. So D2 will not work as well as D4. So how does current flow occurs? Here from point A through D1, as D1 is forward biased, it is working. Current will come up to point M. It can be divided into 2 ways, through D2 and through RL, but D2 provides reverse bias, high resistance, so current will flow through RL. It will come up to point N. Again, it can be divided into 2 paths, D4, D3, but D4 is right now in reverse bias. It will provide high resistance, so current will not go through D4, but it will flow through D3. So here it is. What happens in positive half cycle? During positive half cycle, A end is positive, current flows through D1 up to point M, then through RL up to point N, through D3 and back to point B. So during positive half cycle, D1 and D3 they work, whereas D2, D4 remain reverse bias. Again, whenever the negative half cycle appears, A end becomes negative and B end becomes positive. So here it shows D4's cathode is here becoming negative, anode of D1 becoming negative, anode of D2 becoming positive and cathode of D3 becoming positive. So which diodes will work? D2 whose anode is positive and D4 whose cathode is negative, whereas D1 its anode has become negative and D3 its cathode has become positive. Both are getting reverse bias. So how does current flow occur? Here from point B, whenever current flows through D2 comes point M, it can't flow through D1 as it is reverse bias. It will follow the path of RL. Then again it can be divided into 2 paths, but D3 is reverse bias, so current will move through D4 and it will return to negative terminal. So during negative half cycle from point B through D2, current will come up to point M. Again the direction remains the same. It is not flowing from N through RL towards M, but again it flows through RL in the same way from M to N. But right now the paths of diodes are different. Here D2 and D4 will conduct D1 and D3 will not. In this way, as the current direction in negative half cycle is the same as from the positive half cycle, here it is the output during negative half cycle. Here D2, D4 conduct for positive half cycle, D1 and D3 for negative half cycle, again D2, D4, again for positive half cycle, D1, D3. So, as we started discussing this particular bridge rectifier, here we found a parallelogram, means D1 and D3 they appear to be parallel to each other and D2, D4 to be parallel to each other. But what happens in the current conduction path, D1 and D3 for positive half cycle, they appear in series. हे दोन्ही series मध्ये आले. During negative half cycle, again D2 through RL through D4 back to A, D2, D4 they get connected in series. Appearance is like parallel, but when current flows, both those diodes, conducting diodes, get connected in series. So for a single diode, how much is the minimum voltage requirement? 0.7 volt. So whenever two diodes are in series, minimum 1.4 volt is to be utilized to overcome internal depletion layer. So the drawback of this bridge rectifier is, if it is to be designed for low DC voltage, it is not suitable because minimum 1.4 volt is to be utilized for the overcoming factor of internal depletion layer when those two diodes get connected in series. That is the main drawback. Or else the advantage is it doesn't need center tap transformer. It can work on normal transformer. Even though without transformers, these four diodes, they can work. So what is VDC? Again 2 Vm upon pi, 0.636 Vm. VDC either IDC into RL or 2 Vm upon pi. IO current rating half the IDC. IDC can be calculated if RL is mentioned, VDC upon IDC. So half of that the current has to be handled by each diode. PIV, the total secondary voltage, is useful for forward bias as well as for reverse bias. So peak inverse voltage for every diode required is Vm, and F out for one cycle it gives 2 output cycles. So output frequency is double of the input frequency. If input frequency is 50 Hz, output frequency becomes 100 Hz. And the rectification efficiency to transfer AC power into DC, that ability is nothing but the rectification efficiency, which is 81.2%. So in this way, for every electronic circuit, whenever there is a need of a DC power supply, AC is to be converted into DC by using either half-wave rectifier, full-wave rectifier or bridge rectifier. But bridge rectifier is not suitable for low DC voltage as two diodes conduct for either half cycles and they need minimum 1.4 volt to overcome internal depletion layer. In this way, such bridge rectifier circuit can be used where center tap transformer is to be eliminated, as well as output is twice of the center tap transformer. VDC, total secondary voltage is 40 volt. Here also total secondary peak voltage is 40 volt. But for center tap full wave rectifier, only half, 20 volt gets used for the conducting stage. Here total secondary voltage, so double voltage is appearing at the output of bridge rectifier as compared to full wave rectifier using center tap, as well as PIV rating in case of center tap full wave rectifier was twice Vm. Here it needs only Vm as the PIV. Again PIV rating should be greater than Vm. Stepping up or stepping down is not necessary. Then also directly 230 volt can be given to such bridge rectifier circuit. This is available in an IC form. In this way, we can study bridge rectifier as compared to full wave as well as half wave. So our next session will be the comparison part of these three rectifiers. Thank you.